Okay, so it's my pleasure to introduce our next speaker. So Iva Halacheva will be speaking about the cactus group, crystals, and perverse equivalences. Thank you.
Thank you very much for the introduction and for the invitation. I was actually a participant in one of the previous junior trimesters in Bonn, and I have very fond memories. And I'm sad that we cannot be there in person at the moment, but I hope to return soon in the future. My talk will definitely include some categorical ideas and actions, more in the direction of crystals and perverse equivalences. And this is joint work with Tony Licata, Ivan Losev, and Oded Yacobi, so spanning 2 continents, so North America and Australia. And so I'll start with the big picture landscape of where this project fits. And then I will go on and start from the beginning and say a few words introducing some of the notions. So we start with a simply laced Kac-Moody algebra. So for our purposes, we'll be only considering the simply laced case. And in that setting, so we can consider the category of representations of the quantum group of G. And so work of Kashiwara has described a way to go from so a quantum group representation and obtain a crystal which encodes the information of the representation. So this is work of Kashiwara for the Q. So we can think of this as the Q goes to 0 or limit or freezing the module in more informal language. And on the other hand, Lustig tells us that given such module, it carries certain Braid group symmetries. So given a module of the quantum group, we can construct an action of the Braid group on it. So have an arrow to G Braid group actions. And going from crystals, here in joint work with Joel Kamnitzer, Lonya Rybnikov, and Alex Weeks, we describe how to get a cactus group action on a crystal. So this is mimicking the Braid group action on the quantum group module. And so we would like for there to be a way to go directly from a Braid group action to a cactus group action. And I think this diagram should commute in some sense, but I'm not sure of how to formalize this arrow. So I'll just put it as dotted. And if some of you have some suggestions on that, I would be very happy to hear them. So this is the classical setting. Now let me go to the categorical level. So we have, on the other hand, categorical UQG actions, or where we have a category with a certain notion of an action of the quantum group. And so that decategorifies when we take the Grothendieck group to a representation for the quantum group. And so we also have the notion of categorical Braid group actions. So G Braid actions, where, so let me mention some work here. So work originally of Chuang and Rouquier described how we can get a categorical braid action using so-called Rickard complexes. Use a different color for them. And they were constructed in work of Chuang and Rouquier, and Cautis and Kamnitzer showed that they actually satisfy the braid relations. So I'll put them here in this diagram as well. And so here again, this decategorifies to the usual notion of braid group actions. And just to introduce a few more details in this picture. So, from categorical quantum group actions, so there's work of Lauda and Vazirani, which tells us that we can get a crystal on, so given a category with the quantum group action, if we take the simple objects, then they carry an action, they carry a crystal structure. So this is work by Lauda and Vazirani. Okay, and so where our project fits is on the other side. So we want to consider certain Rickard complexes, namely those that correspond to a positive lift of the half twist. And we want to show that they realize a cactus, the same cactus group action that we get on this. So the action by the Rickard complexes agrees with this action in work joint with Kamnitzer. Oh, sorry, I put Lonia's first name. It should be Rybnikov and Weeks. So we're interested in this. So building a bridge here using perverse equivalences. Okay, and this comes from the half twist, which I'll talk about more in detail in a moment. Okay, so this is the landscape, and this is where this project fits. So let me go back and start from, well, the beginning and say a few things which I think everyone in the audience here knows, but if not for anything else, then at least to establish some notation. So what is a categorical G action? So let's warm up with SL2, and this is very rough, so I'm omitting some technical details. I hope the audience is not offended by that. So just non-categorically, suppose we have an integrable representation here of SL2. And so we have the Chevrolet generators E and F, which take us between the different weight spaces. And they satisfy this important relation, which plays a key role in the categorification. So then a categorified SL2 action for our purposes is going to be an abelian category, which also comes with different components, where each of the components decategorifies to the corresponding weight space. And we'll also have exact endofunctors, E and F, where E goes, we can think of, so I'm omitting the projections here, but we can think of E as taking the nth weight category to the n plus second, and F taking the nth to the n minus second. And we also require some further information, which is again relating to how, in particular, this equality categorifies. So we want some natural transformations which tell us that, E and F are adjoint. So those are the first two we will want. So the unit and co-unit of a junction. Let me write the co-unit first. And we also want certain natural transformations from E to E and from E squared to E squared. And so we can use those now to categorify precisely that relation that was given in the classical setting. And so this is again work of Lauda, Kovanov-Lauda, Chuang, Rouquier in particular. And so all these natural transformations are giving us this deeper information on how the functors, exact endofunctors are related. And the bonus here is that we also get, so these X and T give us an action of the nil-affine Hecke algebra on powers of E. Okay, so that's the SL2 picture. And maybe let me just give a quick example. So if we consider the adjoint SL2 representation, then we have the two 0 and -2 weight spaces, which can be realized as, so these are both modules over C, and the 0 weight space is a modules over this ring. And then the raising and lowering operators are just induction and restriction. And for instance, the action of, so the natural transformation X here acts by multiplying by little x, and here by multiplying by, whoops, sorry, I meant to put that on top. It acts on the raising part, so it acts by multiplying by x. And here by multiplying by -x. Okay, so more generally, I'll just use a quick way to give the general setting. So we have two categories, which categorifies. So here we have Lustig's idempotent form. So we, in particular, have a system of idempotents, which I am not denoting for simplicity here. So this two category has objects given by elements of the weight lattice. One morphisms we can think of as the Chevalier generators, so the EIs and FIs, and two morphisms we can think of pictorially. So these natural transformations, which I've drawn here. And so really these are diagrams with crossings, cups and caps, and beads, which satisfy certain relations. So there's this really nice pictorial picture here. And again, all of this is due to Rouquier, Kovanov-Lauda. Oops. So we have these two morphisms, which generate, these pictures generate the two morphisms, and they have to satisfy, so here I'm not going into a great detail, but the KLR algebra relations on the upward pointing strands. And we also have some further relations such as biadjunction and so on, which I'm not going to list. Okay, so then in this language, a categorical G representation is a two-functor going from this two category to some other appropriate two category. So, okay, good. So, and so I've described here the non-quantum setting, and there's a graded version which categorifies the quantum idempotent form. So, And in our paper, we're using the quantum setting, but for the purposes of this talk, I'm going to just say everything without that. Okay. So let me move on to Rickard complexes. So again, I'll start with the SL2 setting. So given the Lie algebra SL2, whoops, sorry. Let's consider the element which is the lift of just the simple reflection, which we can also realize as the product of the exponential of minus f times the exponential of v times the exponential of minus f, which lives in SL2. And so then S restricts to an isomorphism on the weight spaces of a given SL2 representation V. And it has a really nice form when restricted there. So let me tell you what it looks like on the minus n weight space. So it's just the sum of minus 1 to the k. And then we have the divided powers here of E m plus k f k. And so this gives us an isomorphism from V minus n to Vn. Okay. And so consider now category C. So in our case, an abelian category that categorifies this representation. And again, work of Chuang and Rouquier gives us a categorification of the Rickard complex. So let's consider, and this for me is theta. I hope that's readable. So consider the following complex of functors, which is made up of these individual pieces where the nth piece goes from complexes in the minus n weight space of C to complexes on the nth weight space of C, which is given as follows. So here we have the functors E and F, and so we have the divided power functors. So it's each of these is a complex of functors where I underline in red the 0th homological degree. And so the ingredients to construct this are, so to construct the divided powers, so these are defined using the action of the Nil-Affine-Hecke algebra. And the differential comes from adjunction. Okay, so this theta now in particular is inducing a self-equivalence on the bounded derived category of C. And by restriction, it induces an equivalence on the bounded derived categories of these weight categories, and it decategorifies to this element S. So this is in the case of SL2. And now we're hoping to understand it more generally for arbitrary simply laced G. So let me just give another quick example of what this theta looks like. So consider again the adjoint representation for SL2 and consider the ring R here. And suppose N is an R module. So then we can look at theta 0, for instance, which goes from the bounded derived category of C0 to C0. So namely, this goes from, so if you remember the earlier example, this goes from C0 is just R modules here. And so it takes this object N to the complex, which is, sorry, there's a question. Two-sided tilting complexes. I believe Yes, but maybe I'll say that for the break. So there's also work of Losev, who uses Rickard complexes, and I think there the connection is easier to see. But yeah, for Emily's question, sorry. Okay, so so what does n go to? So it goes to the complex, which has R tensor n in the -1 degree and n in the 0th degree, and this is just the action map. Okay. So this is an example of the Rickard complex in the case of SL2. So let me move on now to a slightly different topic. So one property that this Rickard complex satisfies is that it's in fact a perverse equivalence. So let me say a few words about that. So suppose we have, again, abelian categories with filtrations by Serre subcategories. And suppose we have a derived equivalence between their bounded derived categories. And we have given function from the indexing set of the filtration to the integers. Then we call this derived equivalence perverse if it satisfies the following two properties. So note first of all that these bounded derived categories are triangulated, and so we have a shift functor. And perverse with respect to this data, the filtrations and the perversity function, means that f shifted by this value minus p of I restricts to an equivalence between the following two categories. So let me write it down and I'll say what that is. So on each side here we have, so dB sub A I of A is the thick subcategory of dB of A, where the complexes have cohomology concentrated in AI. So this is cohomology concentrated in AI. So we take that thick subcategory, and so F shifted by this value restricts to such an equivalence. And then we have an induced equivalence on the quotient triangulated categories, which the second condition is that this induced equivalence gives an equivalence of their hearts with respect to the induced T structure. So this is what it means for a derived equivalence to be perverse with respect to this data of the filtration and the perversity function. And maybe let me say, perhaps before we take a break, I'll give an SL2 example. So we start again with the abelian category C with the categorical SL2 action, and consider the collection of symbol objects of C. And we define two filtrations just given by the action of the E's and the F's. So we take the simple objects which are killed by Fi plus 1. And the other filtration is the simple objects which are killed by Ei plus 1. Oops. So, and they in particular induce filtration on C by just looking at the Serre subcategories generated by these sets of simple objects. And so proposition by Chuang and Rouquier is that this Rickard complex is perverse with respect to these two filtrations and the identity perversity function. Okay, maybe this is a good place for the break.
Yes, thank you, Eva. Yeah, that's good. And there was the question by Emily, if you wanted to respond to that.
Let me see. Emily, I think you're right that they're related to the two-sided tilting complexes. I don't think I can give that, that much information further.
I was just wondering because, we're doing a block theory learning seminar here, and we had Rickard equivalences yesterday, and so it's something from representation theory of finite groups, and it's a way to show that two blocks are derived equivalent, so two categories of representations are derived equivalent via some particular type of two-sided complex, but it's a different definition, so I just wondered what the relationship is.
That's a good question. Maybe I don't know if I can answer it in detail. I can mention some references. So for instance, there's this paper by Chuang and Rouquier on derived equivalences for symmetric groups.
That must be where it came from then, yeah, that would make sense.
So if I can comment, so they I think when maybe should you stop using Rickard complex, the term that's our fault with maybe Joe Chuang, but we use it for different things. We've used it for different things. So the way it's maybe is most reasonable is Rickard's theorem on the Moita theory for derived categories and its adaptation. And so it's been used by having one of those complexes of bimodules that does not just an equivalence of derived categories, but an equivalence of homotopy categories. Okay, so that's a very useful term, and I think it's been people doing finite groups, modular representation. I think I've been using it mostly in that sense. So you want more than the fact that if you tensor your complex and the dual, you want it to be not just quasi-isomorphic to the identity, but really homotopy equivalent to the identity functor. So it's a stronger requirement, which we could not prove with Chuang, but that has been proven recently by Laurent Vera. So it's, I don't think he has put his preprint on archive yet. So one can prove that it's not just an equivalence of derived categories, but an equivalence of well, actually, we do prove that it's an equivalence of homotopy categories, but what Vera proved is that it's true already at the level of the two category. Okay, so if you do the two category at the two categorical level, you have your E's and F's. You have this unbounded complex. You tensor it with the dual. This is homotopy equivalent to the complex just in degree 1, in degree 0, not just derived equivalent. So Rickard complex usually, I think these days would refer to homotopy versus just derived.
Thank you. Yeah. So you're saying I shouldn't call them Rickard complexes in this setting then? Or?
I think we did that in our paper, but maybe that was a bad idea. Yes, that was
probably. I see. Okay.
I'm sorry about that.
No, fair enough. Because we were also wondering about extending this to the additive setting.
Yes, exactly. So now I think. Now this is resolved by Vera. So I don't. He has maybe his preprint is an archive, maybe not. He's checked that it does work in this additive setting as well.
Okay, that would be great. Maybe if I can get his preprint, it could help us with that.
Yes. Thanks.
Great, thank you.
Thanks, Matthew.
Thanks. Sorry for the longer.
No, that was great. Thanks.
Okay, it is now past, so you're welcome to continue when you're ready, Eva.
Okay, great, thanks. Okay, so maybe for the purposes of this talk, I'll continue calling them Rickard complexes. but I'll try to change or suggest to my co-authors slightly modifying the name. Okay, so so we have this proposition in the work of Chuang and Rouquier, where in the SL2 setting, we know that this Rickard complex is perverse. And so now we generalize this to, so general G. So we consider, let me just unveil the whole thing. So we consider a reduced expression for an element of the Weyl group. And then we can consider the composition of the Rickard complexes for these simple reflections. And that gives us a Rickard complex for W, corresponding to the positive lift of W. And we know that it doesn't depend on the reduced expression because, as I mentioned, Cautis and Kamnitzer show that the Rickard complexes satisfy the Braid relations. And so we show that if we take the longest element of the Weyl group, and maybe I'll remove the mu here. So, and we have a weight of the category C, which carries a categorical action of this Lie algebra G, where G here, as in the beginning of the talk, is a simply laced Kac-Moody algebra, then this Rickard complex from the bounded derived category of the mu weight space to the W naught mu weight space, weight category, sorry, is a perverse equivalence. And maybe I'll say a few words about what the filtrations and the perversity function are in our setting. So we'll use a so-called certain isotypic filtration of these weight categories. So, okay, so let's just for simplicity of notation, take A to be the mu weight space category and A prime to be the W naught mu weight category. And then we have this Rickard complex from before. And so V here is the representation which C decategorifies to, and it's a direct sum of its isotypic components over the dominant weights lambda. And so we're taking the following isotypic filtrations of each of these weight categories. So start with the dominant weights, which satisfy the following two conditions. So the lambda I isotypic component of V is non-empty, and the mu weight space of the highest weight irreducible representation with highest weight lambda I is also not zero. This has to be true for the lambdas. And then we order them in the following fashion. So from lowest to highest based on the height of this fixed weight mu minus W naught applied to the lambda. So this gives us certain filtrations on A and A prime. So let me write them down. So for A prime, for A, first of all, we take all the elements of A, where A here, remember, was the mu weight category, such that the class of M is in the direct sum of the lambda K isotypic components of K going from 0 to J. And similarly, AJ prime is all the elements of A prime whose class lives in the this direct sum of these isotypic components. Oops. Okay, and so one lemma, which is very useful to realize these categories as is, so AJ can be realized as the objects which get killed by a certain number of applications of F whenever you're applying more than the height of mu minus W naught lambda J, just by the ordering of the lambda J's. This will happen, and similarly, AJ prime can be realized as those objects in A prime, which get killed by a certain number of applications of the raising functors. And since the F's and the E's are exact in particular, this also tells us that these categories are Serre. So in particular, AJ and AJ prime are Serre subcategories. Okay, so, and let me tell you what the perversity function looks like. So we define P from the indexing set of the filtration to the integers to be given by, so P of I is just the height of mu minus W naught applied to lambda I. So you can really think of these filtrations as coming from the isotypic decomposition. Okay, so now that we've established that Rickard complexes corresponding to longest Weyl group elements are perverse, from here, we're going to get an action of the cactus group that they define. So let me remind you a little bit about Braid and cactus groups first. So the Braid group corresponding to the Kac-Moody algebra G just has generators indexed by nodes of the Dynkin diagram or simple roots. And the relations are, so the Braid relations where between I and J whenever they're, so the first is the Braid relation between I and J whenever they are connected, and the generators commute whenever I and J are not connected. So this is what the Braid group for an arbitrary G looks like, and let me define the cactus group for a Kac-Moody algebra G. So here the generators are indexed by subdiagrams of the Dynkin diagram or collections of simple roots. And in fact, you can restrict to the case where J is connected in the Dynkin diagram. So it's sufficient to consider those. And there's three types of relations. So first of all, they're all involutions. They commute whenever the two diagrams are not connected with each other. So for all J and K not connected. And so there's a third type of relation coming from the Dynkin diagram automorphism of G, or which is given by, so suppose in this case, let's see, K is a subdiagram of J, or subset of J, and they almost commute, except, so CJ, whoops, sorry. CJ moves on the other side, and the diagram K, so we apply this automorphism to a tau J, which is defined as follows. So on a simple root, alpha J, we can define this automorphism tau J as just acting by the longest minus the longest vowel group element. So for the parabolic corresponding to J. So this is the third relation for the cactus group. And so, as I mentioned, for the Braid group, that Cautis and Kamnitzer in 2010 showed that Rickard complexes satisfy the Braid relations. And so now let me say a few words about the cactus group and how we get an action of the cactus group also coming from these special Rickard complexes corresponding to longest vowel group elements. So I'll first just mention a combinatorial cactus group action. So we have that acting on any crystal, which I'll break up into highest weight irreducible components. So this action is combinatorially defined using so-called generalized Schützenberger involutions, because in type A, they're just the classical Schützenberger involutions. So in each of the irreducible highest weight components, this generalized Schützenberger involution is defined as the map, the unique map which satisfies the following three conditions. So I'm just going to describe how it acts on elements of B lambda. So if we switch the raising operator EI with this C lambda, then that turns into F tau I. So this is for all B and B lambda. And similarly, if we switch Fi with C lambda, this gives us E tau I C lambda, where tau, remember, was the Dinkin diagram automorphism earlier. And finally, it takes the lowest weight element to the highest weight element. So the weight of C lambda B is W naught applied to the weight of B. So these three properties uniquely define C on crystal B lambda, and then we extend, let me just go up here. Then we extend to all of B by just applying to each connected component of the crystal the corresponding C lambda. And then the cactus group action is just defined as, so the J generator acts as CBJ, where, let me say, if I call this CB, then BJ here is just the crystal B restricted to the Dinkin diagram J. So this is the way we define this combinatorial action of a cactus group on any G crystal. And let me just give you a quick example of this for the SL3 adjoint crystal with highest weight alpha 1 plus alpha 2. So the cactus group here, it has three generators. They just correspond to, so you can think of them on the Dinkin diagram. We have C1, C2, and C12 is the one corresponding to the whole thing. And so here is the crystal, and I'll just tell you the action of each of the three generators. So the full, the element corresponding to the full Dinkin diagram swaps the highest and lowest weights here. It swaps these two elements, and the two weight zero elements. For the C1 action, so what we're doing is forgetting one of the nodes of the Dinkin diagram, and so the corresponding raising and lowering operators, and it just swaps within each of these pieces. It does the same operation. So swapping lowest and highest. And similarly for the C2, we're forgetting the other node. And so the action is like this. Okay. Any questions or comments? Sorry, there was something in the chat. Oh, this was the reference. Okay. So, so this is the combinatorial action of the cactus group on a crystal. And so our theorem, which follows from the fact that the Rickard complexes are perverse, is that so since theta W naught J is perverse, so I mentioned it as W naught for the whole Weyl group, but in fact it's true for any W naught for a parabolic. So given that this is perverse, it induces bijection on the simple objects of the category C. So I'll just denote them like this. And this bijection gives us back the same action of the cactus group. So then the map, which takes the generator Cj to theta j, defines an action of the cactus group on the set of simple objects of C, which, as we know by work of Lauda and Vazirani, carries a crystal structure. And so this is the same action. So this coincides with the combinatorial action above. Okay, I think I'll actually stop here, so I'll finish early.
Thank you very much for a lovely talk, and if we can all thank our speaker for the talk. Does anyone have any questions for Iva?
Iva, I have a question going back to your example you did on the crystal.
Yeah.
Yeah. So also when you had just on the leftmost one, the C12 action, does it, so you said what it did on the nodes, does it also swap the blue and red arrows?
So unfortunately it's not, it's only a bijection on sets, so it doesn't preserve the crystal structure. Okay. I should have said that. Yeah, sorry. But the way you can think of it, so yeah, it's not, so it doesn't preserve the crystal structure, but the way you can think of it is, we get from, let's say, or maybe I'll pick a more complicated one. So let's say this one came from, let's say F1 and then F2 applied to the highest weight. And then, so using the two properties, or the three properties, in fact, we know that this highest weight goes to the lowest weight for sure. And then F1 becomes E2, and then F2 becomes E1. So really, this element, that's how we figure out that it gets mapped to the one in the other one in the zero space. I don't know if that quite answers your question, or?
Yeah, it does.
Is there a version of cactus group for affine type A crystals? So if you took the Dinkin diagram, that's a circle.
So I know it exists. I'm not sure if it's written down anywhere. Potentially in the paper of Losev, but I think the way you define it is just take the generators to be all indexed by all the subdiagrams except for the whole circle.
Okay.
Yeah.
Sure.
So yeah.
Shouldn't this work in general? Like you could take just conditions for finitary subsets, right?
Yeah, exactly. That's what I was trying to say. But thanks for, yeah. Yeah, so in principle, that should work as well for affine type.
Then is it known what it does to the crystals that that I know and love?
I don't think that's written down anywhere. Yeah, that's a good question. I'm not sure. That's been on the very long back burner to think about. But as far as I know, it's not written down. Yeah.
Cool. Thanks a lot.
Mm-hmm.
Yeah, I wanted to mention there's one something a little bit stronger that one could hope to prove, which possibly follow from what you've done. So the notion of perverse equivalences requires some abelian category, some T structure, or you can do something in an additive setting. But if you think of the notion of perverse self-equivalence, this does not require any abelian category. You see, you have a triangulated category T, and you have your filtration.
Mm-hmm.
And what you're asking is that the self-equivalence preserves the filtration, and on each slice, it's a shift by the perversity function, okay?
Mm-hmm.
So then you can ask, you can ask if you have one of those two representations now not on an abelian category, directly on a triangulated category. You can ask if it's perverse in this sense, and so that, or you can ask even directly again in terms of the full two category itself, and you have an additive category. You take the homotopy category, and so you can ask there, is that perverse in some sense? So there are those questions which they may have positive answers as in a rather formal way as a consequence of your results. It's possible that what you've done implies these other things. But self-equivalence, perverse self-equivalence, you can talk of that with that structure, which is a bit confusing maybe in the terminology.
Mm-hmm. Okay, nice, thanks. And you think that also in the if we think about the homotopy category, maybe we could do it in the additive setting as well. I mean.
Yes, that should also, but this should follow from, there might be a way to deduce it from your work. Yes, but yeah, that should be true.
Okay, great, thanks. I'll look into that.
Another question, I mean, maybe this is a bit naive. I mean, I'm not an expert of these in these categorical actions, but I mean, you work over like C-linear categories throughout, right?
Mm-hmm.
I kind of vaguely remember that a categorical isol, like Katz-Moody group action, Lie algebra action kind of forces some sort of semi-simplicity probably or something, but is this, is there a notion if you want to generalize this to positive characteristic, where you just maybe potentially kind of, replace certain direct sums you're forcing to certain filtrations?
That's a very interesting question. I have nothing to say about positive characteristics. I'm sorry. That's a great question, but so far I've only ever thought about over C. But yeah.
Maybe Raphael knows something. I don't know.
Well, in everything you've explained, you never used that. I mean that. Your field at characteristic 0, is it in the older Cautis, Kamnitzer, Licata work? Do they assume Is that where they assume characteristic 0? Maybe that's where it is.
Where they prove the Braid relations, you mean?
Exactly. Is that where they assume? Is that known only in characteristic 0? I don't know.
I would say so. Yeah, I think.
Okay, so but that should be true. But it's okay. It's their proof is not. Yeah, it requires some effort. So it might be difficult or painful to adapt it to characteristic P. I don't know. Yes, I see.
Yeah.
The rest of your work is over any field, I imagine.
Okay.
And I guess the whole framework of categorical Lie algebra actions is, I mean,
defined over Z. Yeah, over the integers. Yes. Over any. Yes.
Okay, I think I shall stop the recording in a second. So thank you again, Iva, for a wonderful talk. And if we can all thank our speaker.